can always interpret this on a graph, f versus x, as a pretty curve. Here's our function. And if we pick a specific point, call it x sub I, and we calculate the derivative at the point, if we draw a line that's tangent to that curve, draw it with a different color, well, that's good enough. Tangent to that point, the slope of this curve is df dx at that point, evaluated at the point x equals x sub I. That's the instantaneous change of the function, right? And in this course, we only do a very, very small number of actual derivatives, right? And so this is just this is kind of our definition of a derivative, but practically, right, derivatives, you're going to do something to a function to make a new function, right? Calculate the derivative of a function. And there's only a couple functions that we really care about in this class. We don't really see that many, the diversity of functions that we see in this class are pretty small. One, of course, is if we take the derivative of a polynomial, just as a reminder, right, if you have x to the n, what's the derivative of this?
Nx to the n minus 1.
Yeah, thank you. All right, and another one we're going to see is the natural logarithm of x. What's the derivative of this? 1 over x. And what's another one that we do? What's the derivative? This is an easy one. What's the derivative of e to the x? E to the x, right? This literally encompasses pretty much every function that you're ever going to see in this class. Right? We're going to see a lot of logarithms when we talk about Gibbs free energy and mixing. We see e to the x already, right? We talked about the Boltzmann equation, that's the e(x) term. And of course, there's always going to be polynomials, right? We're always either we have a function that's a polynomial, or we're approximating something that's a polynomial. And if you want to consider the change of that function, then you always just use this formula, right? Right, and this is mostly in terms of one-dimensional functions, or sorry, single variable functions. This is pretty much 99% of everything you're going to see in this class: polynomials and logarithms and exponents. I don't think you'll ever see a sine or cosine in this class. Now, next semester, you're going to see a lot of sines and cosines. Pretty much, we talk everything in sines and cosines. So we won't worry about the trig right now. Right. So let's just go for the next. Of course, the other tool we learn, which is the idea of accumulated change. And what's the tool we use to calculate that? I heard it. What did you say?
Double derivative.
Well, no, not double derivative. Accumulated is think about aggregate or sum. What do we call the sum of a change? This is the integral. The accumulated change of a function. It's an integral. Right, and I'll explain what I mean by that. So a nice way to think about an integral is to think that you have a function that changes over time or across a variable. And an integral is how much of accumulation of your output do you get as you sweep over the inputs, right? So for instance, the idea is like for work, right? Work is the integral of force times displacement. The integral of force times displacement. So the amount of energy that comes out of a process is the accumulation of the force across the distance that you're applying the force, right? Energy is accumulated force, if you will, over a distance. So again, the definition of an integral roughly is that, again, assume a function f of x. Okay. The integral of f of x dx is equal to the limit as delta x goes to 0, roughly, of the sum of f of x sub I. So this is I equals 0 to some limit, whatever it would be. We'll just say n delta x. All right, so you're basically multiplying the value of a function at a bunch of different points by the distance, the small displacement you're making in the input variable, and then summing over all of it. All right, and graphically, this again looks like the area under the curve. So let me draw my function again. Here's my function, x and f. So if we pick 2 points on a curve, called x sub I, and here's another one, x sub I plus 1. And so the distance between these is delta x. This is f of x sub I. This is f of x sub I plus 1. Right, and the integral between these 2 points, once you take the limit, is just the area under the curve. All right, so if we think about this, if we think about the function as being the force, this is displacement and this is the force function, right? How much force is being applied as a function of distance. The amount of energy we consume in this gap is the integral from the initial point to the final point. All right, so this is the work from xi to xi plus 1. All right, it's the accumulated force across the distance. All right, so when we think about when we want to think about how something changes as we change a variable, we want to calculate a derivative. If we want to think about the change, how the change of a function changes as you change position, you think of a second derivative, right? The curvature of the right. How much is the slope changing as you move, right? That's the second derivative of a function, and an integral, of course, is just the accumulated change over a function. Questions so far? This is probably all nice and easy review. Right? And of course, again, we only care about a couple of functions. So, what's again, just as a useful thing, what's the integral of a polynomial? X to the n. X to the n plus 1 divided by n plus 1. Right? And what's the log? What's the integral of a logarithm of x? This one's a good one to know. Any guesses? Anyone know remember what it was? Oh wait, sorry. Yeah, this is actually x ln x minus x. That's not what I meant. Sorry, that's a tricky one. I meant this one. 1 over x dx. What's the integral of this? Yeah. That's the more useful one.
Doesn't it also have the absolute value?
Yeah, it does. Yeah, so because you don't want this to be negative, right? Right, you don't want this to be negative, yeah, so it has to be absolute value. We're pretty much always going to deal with positive values in physical chemistry because there's no negative pressure and no negative volumes, so it's not a big deal. Very few negative numbers in this class, except for energy. Right, so that's basically 90% of all the integrals you ever have to take, and 90% of the derivatives you'll ever have to take. Right, so this is single variable calculus. But the fact of the matter is that we deal with equations of state, right? For instance, the ideal gas law is a function P of pressure that's also a function of temperature and volume as well as moles. Right? It's a multivariable function. So we want to think about how we take derivatives of a multivariable function. And what we'll find is that it's really no different than taking a single variable function. We just have to make some assumptions about what we're taking changes with respect to. So let's look at the ideal gas law. Let's not use pink. I want to keep my pink alive for a while. All right, so let's say here's the ideal gas law. P is equal to nRT over V. Okay, well, whenever you want to take some derivatives of this function, how does P change as we change another variable? So for instance, let's consider how P changes as a function of temperature. Well, that's tricky because we don't know how N or V are changing. Right? If we could, for instance, fix N and move V, and T will change, right? T is a function of V, and V is also a function of T. Right? So V nRT over P, right? And T is equal to PV over nR, right? So they're all kind of related to each other, right? So as you change one, the other one might change as well, right? So you'll have to deal with the fact that there's these variables talk to each other and that they both change as you change them. So what we want to do instead is look at how pressure might change as temperature moves, but holding everything else constant, right? So let's hold, for instance, N and T constant. Right, so they stay still. They're not moving. They're just numbers fixed to some value. And the way that we write the derivative, we write what's called a partial derivative, which means that we're looking at the change of the function p, or a part of it, right, which is the motion of the change in p as t changes and none of the other variables, right? So partial means, in some ways, only some variables are changing. Okay, so when we want to hold this constant, we rewrite this with a curly d instead to indicate partial. dp dt. It's just a notation change. And then typically we mark in subscript the things that we're holding constant at the bottom. So if you look at Atkins or in my notes, you'll see things like this all the time. You see curly, a partial derivative with some subscript, and the subscript is what variables are being held fixed. Let's look at this on a graph. We can understand this a little better. Now this is going to require me to draw a 3D graph, which is going to be a miserable experience. So let's try it. And you can all laugh at me about how bad I am at drawing stuff. So let's say we have a curve that is a function of t, v bar, right, which is v over n. I'm just going to combine everything together into one. And the y-axis, the z-axis, maybe is something like is pressure, right? It's the output. I'm going to draw it like a contour map instead of 3D. So I'm going to show you a projection of the 3D plot along the VT plane. Right, so maybe it looks like this. Right, and just before we can draw contours, right, we can draw hills like a topographic map to show height or distance in P. All right, maybe it looks like this or something. And just for fun, we'll add another contour here as well. All right, so these contours indicate height out of the board. All right, so as we go up in this direction, P is increasing. This way. All right, it's not a real function. I'm just drawing something here. All right, so we're curious, like let's say, for instance, we pick a point on this curve, and we're curious about how the function changes as we change temperature and volume at that initial point. So let's say we're right here. All right, so this is P of some t, we'll call it t sub I and v sub I. All right, at the coordinates v sub I, t sub I. All right, and we're curious about how this function, what the instantaneous change of the function with respect to its variables are at that point. Well, we have an option, right? We can do it along the t-axis or the v-axis, right? So the actual change of the function is going to be a vector with some t and some v. Let me draw it in a different color. Let's say, for instance, it's in this direction. Right? This is the tangent of this is the tangent line with respect to this point. And there's two components to this vector. There's going to be a component along t, and there's a component along v, dt and dv. This total thing is dp. Right, so change along this coordinate right here, along dt, right? V is not changing. V is constant. V bar is constant along this one, right? So this is taking the slope along this direction, along the t direction, is the partial derivative of p with respect to t, holding v constant. Right, v is not moving, right? So we're taking the projection of that change vector, the vector change, along the constant volume axis, right? The x-axis here. Likewise, you have a partial derivative, right? So the slope here, and along this direction is dp dt, holding v bar constant. And then we can also look along the v-axis, right, where t is not changing vertically, right? And this is going to be the slope of this along this direction is going to be dp dv, holding t constant. Okay. Now, right, so we can measure the change of the function along each of the axes, right? Along each of the coordinates of the system, right? Temperature and volume. And so now the question is how do you measure the total change? Well, there's a really nice formula for it. So let's assume that y is equal to a function f of x and y, or sorry, let's do z, excuse me. So a function of x and y, then the total change of z is dz, and it's equal to the sum of the partial derivatives like along each of the functions. So it's going to be the partial derivative of f with respect to x times dx, holding y constant, plus the partial derivative of the function with respect to y, holding x constant dy. All right, we're going to see this on the next homework. You have to work with this formula, with the ideal gas law. And so to express the total change of a function of its variables, you just express it in this form, right? You take the derivative with respect to one variable, multiply it by the change in that variable, then take and then sum over all the other changes. Right? So we call this the total derivative of f. Right? And each of its components are the partial derivative, right? The sum of the partials gives you the total. So let's apply this now to the ideal gas law. So how does pressure change as we vary T and V? So again, P is nRT over V. So apply to ideal gas law. So the change in the pressure, dP, we'll start with the temperature side, is going to be the partial derivative of the function pressure with respect to temperature, holding volume constant, times the derivative with respect to temperature, the differential, dt, plus the derivative of pressure with respect to volume, holding temperature constant, dV. Okay. Now all we have to do now is calculate these partial derivatives. And the way you calculate a partial derivative is the same as you would take any other derivative. You just assume that the other variables in the function are just constant. Right? So let's look at dP dt, for instance. Right? P is equal to nRT over V. So in order to calculate dP dt, we take the derivative of this function with respect to t, holding v and n constant. I'm going to simplify this by getting rid of this and writing v bar. So what's the derivative of RT over v with respect to t? Right. It's r over v bar, right? Because this is a function that's linear in t. Right? This is t to the 1 power. It's a linear polynomial. Right? And the derivative of a linear function is just a constant. It's just 1. You're just left over with the coefficient on the outside, which is r over v bar. And now let's do it with respect to volume. What's the derivative of this with respect to volume? Exactly. Right? This is the same, just as a reminder if no one sees that yet. We could rewrite this as RT V bar minus 1. Right? It's a polynomial minus 1 power. Call that a polynomial. Right? We bring this down and subtract 1 from the power. So that's minus RT V bar to the minus 2. Right? So we get rid of this minus because there's a plus, there's a minus sign here. RT over V bar squared dV. Right, so this is the total change in the pressure as a function of its variables. So if we jiggle temperature a little bit, so for instance, let's say we change temperature by 1, okay? So this is dt is 1. Then pressure is going to change by a factor of r over v bar. Right? Let's remember that v bar, just so is volume over moles. No, it's not. I always get that wrong. It's N over V. It's the number of moles per unit volume. And this is proportional to 1 over the density. Right, so as molar volume increases, the density decreases. Right, because it takes more volume per unit mole, and it's less dense. Meanwhile, wait, hold on a second. I always get this confused. Liters per mole. Sorry, I have this wrong again. Volume, there we go. Volume over N. I got this wrong yesterday too. I keep screwing it up. Right, so if this number is large, that means it takes a lot of volume to get a mole. So that means the density is low. So large V bar means low density, and small V bar means high density. This is a good way to think about it. So let's look again at this equation here. Let's hold V constant, so we're only looking at the dt part. Right, this says that dp and dt scales are over V bar. So if V bar is large, which means you're at low density, then this is small, right, because V is large compared to R. So when you change dt by 1, you're dividing by a large number, so dp doesn't change that much. All right, so at low density or large molar volume, pressure doesn't fluctuate very much with respect to temperature. But if the gas is very dense, this is a small number, so dt scales much more like dp, so pressure changes much more aggressively with temperature at high density. Likewise, you can do the same thing as you change the molar volume. Right? The equivalent of changing the molar volume would be to keep the volume constant and pump moles in and out. Right? You pull moles out or pull moles in at constant volume. Right? So as we start to fill the system with more moles, or reduce the volume, however you want to look at it, the pressure is going to change as minus V squared. We also have to account for the fact that there's temperature, right? So inside of this equation, we know exactly how volume and pressure are related to each other instantaneously, because this coefficient on the outside tells us how they scale, right? If V bar changes by 1 unit, then dP changes by 1 times RT over V bar squared, right? So you know that the change in pressure might be more aggressive at small v or high density, right? Because V bar squared is going to be a small number. Any questions about that so far? Okay. This is a really important equation to write down and to remember that you can always express the total change of a function as the sum of its partial changes. And we're going to come back to this a lot because we're doing first law, we're doing the second law, we're going to be talking about changes in the system, we're talking about processes. And so we're going to be interested in how, for instance, energy changes as a function of temperature, or how energy changes as a function of volume or pressure. For instance, we're going to learn this very soon, but the heat capacity, we're going to learn there's 2 different types of heat capacity. We've already mentioned it a little bit. There's what's called the constant volume heat capacity, and that's the change in the internal energy of the system as you change temperature at constant volume. Right? It's a partial derivative of energy with respect to temperature at constant volume. And there's also Cp, the constant pressure, which is the slope of energy with respect to temperature at constant pressure. In reality, energy is a function of volume and pressure at the same time. Right? So we can express the change in energy with respect to temperature, volume, and pressure using Cv and Cp. But again, the math gets complicated when we've got multiple things going around, which is the whole point of why we did isothermal and isobaric and isochoric and adiabatic expansions, so that we don't have to, we can just sit on one formalism and not have to worry about the other things moving around. Okay? So that's really all the calculus you have to know for this class. There's one more thing that I don't think we're really going to do a lot of multiple integrals in this class. I really can't think of a place that we do them anytime soon. We do single integrals. Do we do multiple integrals anywhere? I don't think so. So I won't go over multiple integrals, but if we get to it, I will. Right now, we really care about change. We talk about derivatives. Derivatives are the important tool in this class. Next semester, integrals become much more important. So next semester is an integral class, but this semester is a derivative class. Any calc questions, Megan?
Why are you able to do nRT, like PV nRT over V? Why is that able to be as a single variable, like t to the 1, instead of having to do the whole fraction derivative?
I don't know what you mean.
So like for sometimes when you do calculus for a derivative, you would have to like top derivative of the bottom minus bottom derivative.
Oh yeah, but the thing is in a partial derivative, you're holding volume constant. So it's just a number. You're not, the system, the idea is you're assuming that volume's not changing. So if you did that, all of the changes in volume when you do that term go away.
Okay.
Yeah, it just goes away because the V's not changing. So any terms that are dependent on dV just go away because dV is 0. So that's the advantage of a partial derivative, is that you can take derivatives of multivariable functions, but only do it one variable at a time, holding all the other ones constant, and that simplifies the math significantly. And the idea is that you can separate the total change of a function into a sum of the partial changes, so that you have to do, for an n variable function, you only have to calculate n partial variables, partial derivatives, and you know exactly how the function changes as a function of all of the variables. There is a linear algebra argument to explain why that works. Because, for instance, you may worry that there might be a term, and I think this is the idea that you're thinking, is that there are going to be cross terms like df dx partial x y dy plus df dy times dx, where you have the change in y times the partial change in x. You can show that these come out to 0 with linear algebra, that these turn to 0 for these functions. So we don't have to worry about them. So in some ways, the total derivative is a linear function of the partials. Right? So we don't have to worry about cross terms at all. You can always get rid of the cross terms. So when we take one partial change, we don't have to worry about the changes of any of the other variables in the function. Does that answer your question?
Yes.
Okay, cool. Yeah. That math's a little beyond this, but you can trust that that's the way that works. There's one more rule I want to teach you. I don't know if it'll ever come up, but I just want to remind you of this because it's actually really, really useful. I think we might mention it at some point. There's a second derivative rule for partials. So for instance, imagine that we take the partial of pressure with respect to volume, and then we want to take the derivative of this function with respect to temperature, a mixed double derivative. So this would be the second derivative of pressure with respect to the change in both variables. It turns out that this is the same as the opposite. So that the temperature derivative of the volume derivative is the same as the volume derivative of the temperature derivative. It's symmetric. That's a small factor. I don't think we're only going to look at second derivatives a couple times in the class, but that's a nice rule to remember. So you can always, it doesn't matter which order you do them in, it's the same. There's also a rule for triple derivatives, but I won't teach it. I don't think we'll ever see a triple derivative in this class. It might be also, and this is a really nice thing, I'm going to mention something about double derivatives while we're here. I want to talk a little bit about the idea of a second derivative because it's actually kind of a nice graphical, there's a graphical explanation for a second derivative. I mean, I'm sure you've seen this before. Let me do a different curve. And this kind of ties into the idea that we, in the critical coefficients problem 2 on this current homework, something like that. A function like that, so x and f of x. Let me make this a little shorter, sorry. And let me do it in a different color. That's a little better. So the first derivative again tells us something about the slope of the curve at this point. What does the second derivative tell us? Well, the second derivative tells us something about the curvature of the function at that point. So for instance, if I were to instead draw a parabola that's tangent to this point, that, if you think of this parabola as being g of x equals ax squared plus bx plus c, the a is proportional to 1/2 the second derivative with respect to the variable. Right? So it tells you something about how fast not only how fast is the function changing, but how fast is the change changing. So for instance, at the critical point of the van der Waals of a van der Waals gas, you have a function that looks like this. Sorry. I want to do V versus P, sorry. You have a function that looks like this at the critical point. This, and what we showed is that at the critical point, which is this place right here, which is VC PC, and this is at temperature TC, right? Everything's fixed at temperature TC. And here the slope of dp dv is 0, which means that if I were to draw a tangent line, it would just be a straight line through here. But also that the second derivative with respect to volume is also 0. And what that means is that if you were to draw a parabola here, there wouldn't actually be a parabola because the x squared coefficient is 0. There is no curvature here. Because if you look left at this point, the curvature of this function is in this direction, and at this point the curvature changes sign. So at this point, the second derivative is 0. There's no curvature at that point, which means that there's no at an approximate level, there's no quadratic function that can. It's just 0 there. It's just a line. Right. So the sign of the derivative. The sign of the second derivative tells you about how the function's curved, and it tells you about how the change is occurring, right? So if you think about the slope of dp dv, it's quite sharp on the edges, right? But as you start to approach this, the slope starts to get narrower and narrower, and then it starts to increase again, right? So in some ways, this is somewhat of a stable point, right? There's no effective change there at that point, right? So if your system sits here, what it means is that it's what we call a metastable point. If you jiggle it a little bit, it's just going to fall down this way or go up this way, depending on which way the system moves. But this is kind of like a stable point. It's called a saddle point. And so the system can exist kind of stably at this very single one point right here. And that's because the derivatives are 0. It's basically a flat region. It's one point that's perfectly flat. So the second derivative tells us a lot about the curvature of the function. And that tells us a lot about what's going on dynamically in the system. Right? That if there's a place where the second derivative and the first derivative is 0, in some ways that's what's called a metastable state, which means it's stable only at literally one exact point. And we're going to see metastable positions all the time, metastable things in this class. That's just kind of an advanced idea, something to keep in mind. I think this is a really good way to think about the second derivative as the way that it's the rate of change of the change of the function. Right, so looking for where it stops, you know that something weird's happening here, or interesting. Any other questions about this? Okay, that's all I have to say about partial derivatives for now. Pretty much now have formulas for literally any sort of derivative you're going to do in this class. If we find some more complicated ones, I'll bring it up as we come across them. Now this is kind of a useful thing to talk about because what we ended up with at the end of class yesterday was looking at isobaric processes. All right, which again is that the change in pressure is 0. And I came up with that, well, we had a problem. Let me find it real quick. We had a problem that the change in energy for an isobaric process is a little bit of heat and a little bit of work. Remember, there's a factor of T here. Yeah. All right. A little bit of heat. Yeah, and our delta. Sorry about that. It's a little bit of work and a little bit of heat. All right. So any sort of isobaric process is going to have a mix of the two. Right? And depending on which path we take, we're going to get a lot more heat or we're going to get a lot more work. Right? Depends on which path we want to take. If there's a lot of V or a lot of T. So that's not very helpful. Right? We need to do something a little more interesting than that. And so the thing that we came up with, or kind of introduced into class, is the idea of enthalpy. Right? And I defined enthalpy with this strange equation, which is H, which is the enthalpy, is equal to the total energy of the system plus P times V. Now I just kind of made this up out of nowhere. Right? We went from this to this. And the question is why is this useful? And because there's no real context for this, right? In some ways we call this what's called an ansatz. An ansatz. This is just like a guess. An educated guess function. Where we say, okay, well, let's try this. Let's add some things together and see what happens. So we come up with an ansatz, which is to add PV, which is the energy required to maintain the pressure and volume of the system, plus the total energy. Right? We get this function H. And it turns out that H, as we'll find out, H is a state function. So it's path independent. So all we have to do is measure H at the beginning and H at the end. It doesn't matter which way the system goes, delta H is always the same. But the question is how do we interpret what the physical meaning of H is? Right, what does it matter? What does H tell us about an isobaric process? So it's nice that we talked a little bit about derivatives and changes because we'll need to use that to be able to figure out what H has to do with energy. And so what I want to do is I want to take a system with enthalpy H, and I want to perturb it. So H prime is equal to H plus dH, right? We're going to put a little bit of enthalpy into the system. Right? There's a small amount of energy. Okay, so how does the rest of the equation change? So let's do that. So let's do H plus dH is equal to, and now we apply the function. Well, U might change a little bit, so U plus du. Maybe pressure changes, and maybe volume changes. Good luck, Sophie.
Thank you.
Okay, we don't really know which one changes, but maybe they all change. Right? dV could be 0, dP could be 0, right? But let's just keep them all regular, right? So we change H, that means all of them are probably going to change by some amount. So let's expand this out a little bit. Let's FOIL this. Of course, I'll add the U plus du here. Let's FOIL this out. We get P times V. We get, let me make sure it's in the order that I have it, PV, and then we get P times dV, and then V times dP, and then V dV. Did I get that right? No, sorry. I apologize. let me go back again. So PdV, VdP, and then the mix, the cross term dPdV. So let's rearrange these terms a little bit. Look, there's a U and a PV here, right? That's enthalpy. So we'll recombine those terms into a part. We have a change in U. And then we got some terms of volume and pressure. Right? I'm not sure what to do with those yet. Well, look, so now we have an H here and an H here. So we have H plus DH, right? U plus PV by definition is enthalpy, plus DU, plus some terms that relate to the change of the state of the system, right? The pressure and the volume. Well, look, H can go away now. Right? So the change in H is equal to the change in energy, internal energy, plus some changes in the state. How pressure changes and how volume changes.
There's not two VDPs.
So we got PV, VDP, or sorry, let's do it one at a time. So we have PV, PDV, DPV, VDP, and DPDV. Do I have anything? Does that seem right
Oh,
to you?
yeah.
Yeah, does that make sense? Okay, okay. But we can make a simplification here. The assumption we made is that pressure doesn't change. Those go away. So what are we left with? That the change in energy, or the change in enthalpy, is the change in internal energy of the system, plus the work. Now what we can do is apply the first law. Which is that du is the change in heat plus the change in work. But the definition of work is minus pressure times the change in volume, PDV. It cancels out. So we're left with dq, the change in heat, minus PDV, that's the change in energy, total change in energy, plus PDV. These cancel out. Enthalpy is just a change in heat. So by assuming that pressure doesn't change, enthalpy now is a state function for the heat. Right? Heat is not a state function, as we talked about, right? When you have a process, you can go from point A to point B. So any varying amounts of work or varying amounts of heat, depending on which path you take. But if you simplify to dP equals 0, isobaric, you can define this function h, which is a state function for heat. So enthalpy, the change in enthalpy is the change in heat of an isobaric process. And it's a state function. So if we can measure the enthalpy at a beginning point and an end point of whatever reaction or process that we do, the enthalpy readout is always going to be the heat change. It's just the heat that's being released by the system. All right, we have to go through all this bullshit math to get to it. But we come to a very simple result, right? We actually now have a state function and a very useful condition, right? Anything you do in the lab that isn't under sealed conditions is going to be isobaric. Right? Any sort of open flask reaction or reflux or anything like that is going to be isobaric. And if we can measure the enthalpy, we can measure the heat. And we can do it in a way that we only need to look at the heat at the beginning and the heat at the end, or the enthalpy at the beginning and the enthalpy at the end. And that's how much heat is released by that process. Well, that's very useful. Right? What if we can measure the heat being released from molecules when they react? We can measure if we can measure that change in heat, right? How do we measure a change in heat experimentally?
T final minus T initial.
I'm sorry.
T final minus T initial.
Yeah, but how do we actually measure that though? Like what piece of equipment do we use to measure a change in heat of something? What's that?
Thermometer.
Yeah, thermometer. So if you measure the change in thermometer of a reaction, if it cools down, then that means the enthalpy is increasing or decreasing. Or if it heats up, then that means it's releasing energy, right? That you have a natural release of heat. So by measuring the change in temperature, you can measure the enthalpy. Right? So now all we have to do to measure the change in energy of our isobaric process, we just have to measure the change in the temperature. Or some other way to measure heat released. Well, that's really powerful. Because now that opens us up to being able to measure pretty much anything we want in chemistry. Let me make sure. So let's do an example. Oh, where's 5.1? Oh, here it is. So let's look at this a little bit. Now, I'm sure all of you have seen enthalpies of formation and enthalpies of reaction. You probably did a bunch of that in general chemistry. We'll come to that. But let's look at enthalpy in a more fundamental way. And this is something that you don't often think about. So let me just remind you that change in enthalpy is a change in heat in an isobaric process. And H equals U plus PV. So let's do an example. Here's an interesting reaction that can occur under high temperatures. Take calcium carbonate. What's this? The stuff that Han Solo gets frozen. Carbonate, excuse me. In particular, in the allotrope calcite, right? The mineral calcite. You can convert this under certain conditions into a different allotrope, called aragonite, not to be confused with Aragorn. And these are minerals that you can dig up in the ground. If you've never seen them before, these are some pretty pictures of them if you just Google it. I wish I had pretty pictures of them. One of them is a nice orange color. These each have densities of 2.71 grams per milliliter. And this has density of 2.93 grams per milliliter. Okay, and so you can actually measure the change in internal energy of the system because they're crystalline, effectively. These are crystalline things. It's really easy to measure changes in energy in crystals, as we'll learn once we get to the third law next week. But the molar change, the change in internal energy of this reaction is 0.21 kilojoules per mole. And now the question is what's the enthalpy? So what is the difference delta H minus delta U at atmospheric pressure? All right, so we're going to convert this mineral into another one. And the question is how much of the energy changes heat? Right, so this is the total amount of heat. Right, so this reaction generates some amount of heat. And some of it, of course, is being used some of it's being released as heat, and some of that energy is being used to convert the calcite crystal into aragonite crystal, right? There's going to be some rearrangement of the system. Right? And the question is how much of the total heat being released by this reaction is being used for reorganization of the system from one crystalline form to the other, right? The internal change of the system, right? The work being done, if you will. Right? The system is going to release some heat or absorb some heat to do this. And the question is how much of that energy that changes is being used for heat and how much is being used for work. Right, so just remember that H is equal to U plus PV. So delta H minus delta U is approximately delta PV, right? How much work is being done by the system, right? And of course, work here is the actual physical manipulation of the calcite crystal into the aragonite crystal. Because H, so let's work this problem out. All we have to do is apply this definition. Because H is a state function, all we have to do is that delta H is going to be the enthalpy of the product minus the enthalpy of the reactant, right? The final minus the initial. Right? So we take the enthalpy of aragonite and subtract the enthalpy of calcite. All right, and then we can apply this formula. So this is going to be the internal energy of aragonite. I'm going to write that U sub A for aragonite times the pressure, right? The pressure is constant. It's just a number, 1 bar. We'll be able to plug that in. Times the molar volume of aragonite minus the same thing for calcite. Okay, I'm just going to rearrange things a little bit. This ends up being UA, the change in the energy, internal energy, minus the sum of the PV terms. Okay, and this is delta U minus the sum. All right, so again, we want to measure H minus U, so we subtract from both sides delta U. So delta H minus delta U is just the sum of the PV energies of both species. Right? So this makes sense. Remember, so the difference between the heat being released and the total change in energy is what's left over for work, which is the rearrangement of the calcite into the aragonite, right? The actual chemical work being done to the system. Right, so the difference is just the sum of that work being done. The work being done to the aragonite and the work being done to the calcite part. So we're given densities. We want molar volumes. So here's a nice formula that the molar volume, it's not too hard to work this out, is the molar mass divided by the density. Calcium carbonate has a really, really easy molar mass. This is a really easy one to remember. Does anyone know what it is without looking at it? It's a fun little chemistry fact. Yeah?
I don't know that, but I had a question. Where'd the negative go? It was delta U minus PVA plus PVC.
Oh, sorry. Yeah, where did that go? Sorry, I apologize. I think I'm missing a minus sign inside. Just a sec. Yeah, thank you. I probably just wrote this wrong. Yeah, sorry. Yeah, my apologies. There we go. Thank you.
And it would be negative.
Yeah, and it's VC minus VA, isn't it? We good now? Does that make sense? I think that's right.
Wouldn't they both be negative? Because the negative sign was on the
Yes.
outside of the parentheses?
Yes.
So multiply into both?
Yes. Why is my math all wrong here? H minus U over P A sub A. Right, so let's look. So UA minus UC. Oh, well so that's delta U. And then we have VA minus VC here. Right, there's a positive here and a negative here. So it should be VA minus VC. Do we agree with that? Right, you have a positive PVA minus PVC. Good? Okay. So VA minus VC. All right. Yeah, that looks right to me. Okay, so we can just plug. So the fun thing is that the three significant digits. The molar mass of calcium carbonate is 100 grams per mole. It's a really easy one to remember. I think I learned that. I don't know when I learned that.
Yeah, I
What's
think
that?
The negatives are still like flopped.
Okay, so let's do it again. So
So can we just start
it's not
over?
U, it's just you have UA minus UC. Now you need to have that still on
Oh.
the other side.
oh okay. So
So now you need plus PVA minus PVC, and then
So-
I think in the bottom we just have to look at the next line.
is that right?
'Cause
Yeah,
you
you
have
got
PA,
Yes.
Yeah.
Yeah, that's right.
We like that.
and then I think now we're correct.
Are we all in agreement on that one?
Yes.
Good. We can do arithmetic. Awesome. I can't. You guys can. Right. Okay. So let's look at this, right? So we can factor out the p because the p is constant. It's the same for both. And then we can bring in this formula here. So that's going to be p, the pressure times the molar mass times 1 over the density of aragonite minus 1 over the density of calcite. Now we have to do some conversion factors. So pressure is 1 bar. We should convert that to pascals because everything's in grams and kilograms and stuff like that. So bar to pascal is 1 times 10 to the 6 pascals per bar. We joules. We're going to want to measure things in joules, so we need kilograms. So the molar mass is 0.1 kilograms per mole. And then we do 1 over the times 1 over the density, the difference of the densities. So that's 1 over, I'll just write it here, 2.93 minus 2.71. So let's work out the units for this. These units are in, oh, sorry. Actually, let's do that in grams. Hold on a second. I'm sorry. The grams are going to come into play here. So this is in moles per gram. Oh, sorry. No, it's in milliliters per gram. All right, 1 over density is milliliters per gram. Milliliters per gram. So this needs to be in grams to cancel out the grams, so 100 grams per mole. So we have milliliters times pascals. So we need to convert this into, we just have to multiply by a factor of 100 to convert to liters. And then we have pascals times liters, which is, no, we want in meters cubed. We want in meters cubed. So let's see, 1 milliliter is 1 cm3. And a meter cubed is 1 meter cubed is going to be, so there's 100 centimeters in a meter, so it's going to be 100 cubed centimeters cubed, which is 10 to the 5 centimeters cubed. Okay, so we're going to have to convert by that as well. So let's do this difference in milliliters per gram. Can someone calculate this for me real quick? 1 over 2.93 minus 1 over 2.71. I'll go ahead and do this side real quick. So we have 10 to the 6 Pascal times 100 grams per mole. And then let's get this difference of densities.
Negative 0.0277.
Can you say that one more time?
Negative 0.0277.
All right, milliliters per gram. All right, so the total units of this are going to be, so this is, so let's multiply all this together. This is 1 times 10 to the 8 Pascal grams per mole times 0.0277 milliliters per gram. So let's multiply 1 times 10 to the 8 times this number. Oh, we don't even need to do that. I can do it in my head. This is going to be minus 2.8 times 10 to the 5 Pascal milliliters per mole. All right, we just have to move. We have 10 to the 8 times 1, 2. Do I have 10 to the 7 here? Yeah, no, that's right. Minus 2.8 times 10 to the 5.
I think it's in the 6.
6. Pascal centimeters cubed per mole. Yeah, you're right. You're right. Thank you. Thank you. Yeah, of course. 6. 10 to the 6, and then we need to convert by, we need to multiply it, we have to divide by 10 to the 5 to get it in liters. So that's going to be minus 2.8 times 10 to the 1 joules. So that is equal to 28 joules. Okay, so what this means is that when you convert between, right, the system absorbs 2.1 kilojoules per mole total, right? The energy increases by 210 joules per mole.
Wouldn't it be negative 28?
Yeah, it's negative 28. Thank you. Negative 28. Off by a factor of something here. Yeah, that's right. Are we sure there's not an extra 0 in here? Is it 00277?
No, it's just 1 0.
Okay, all right, cool. So we have 10 to the 6, 10 to the 8, 10 to the 6. Yeah, okay, good. Yeah, that's right. The 28 joules. Right, so the system changes by 210 joules, but the system actually releases 28 joules of energy for work. So the system is absorbing heat, but some of that is being used for work, but only about 10%. Right? So the idea is that so delta H minus delta U is minus 28 joules per mole, right? Which is about 10% of the total energy. Right, so when we measure the heat change, the heat being released by the system, that's not measuring all the energy change in the system. There's a little bit left over that's being used to rearrange the system from calcite to aragonite. Right, so that's a nice thing to know, because what you're measuring is only what comes out of the system. Right, what is being released or being absorbed by the system in terms of heat. Right, this is what delta H is what you measure with the thermometer. And there's a little bit extra left over that you can't measure with the thermometer that's being used to rearrange the system in an orderly way from calcite to aragonite. Okay? Now, I'm going to skip through really quickly because we only have a couple minutes left. I want to compare this. Right? This is a solid-to-solid reaction. Now, what about something like this? What if we do a process where we take hydrogen gas, mix it with oxygen gas, and get liquid, H2O. Right, this is the hydrogen fuel cell reaction. What is H minus U for this reaction? Right, so how much energy is being used for the rearrangement of the system? Well, look, here we're going from a crystalline form to another crystalline form. Right, so the work to rearrange calcite to aragonite isn't that much, right? The atoms might have to be rearranged into a slightly different unit cell structure. But in general, you're not really doing that much to them. They're still going solid. But here you're taking gaseous particles and converting them into a liquid, right? So there's going to be a significant change of work being done by the system. What you can show is that if these are ideal gases, then PV is equal to nRT. So delta H minus delta U. Well, let's say this is at 298 Kelvin. Right, 298 Kelvin. Delta H delta U is going to be equal to the change in nRT. All right, well, T's not changing, R's not changing. So this is delta N times RT. Well, now the question is, what's delta N? Well, what we're doing is we're taking gases and converting them to liquid. So as we go from the beginning to the end process, how many moles of gas are we losing in total? 3. Right, so delta N is minus 3. Right, we're losing 3 moles of gas. Right? Remember, it's ideal, so H2 and O2 are exactly the same. So in an ideal form, there's nothing different between the two, so we can treat them equally. 2 H2 and 1 O2, we get minus 3. Right, so delta H minus delta U is really easy to calculate for a gaseous process like this. It's going to be minus 3 RT. And that ends up being, again, minus 3 times the gas constant, which is 8.3145 times joules per mole per Kelvin, times 298 Kelvin. Someone want to calculate this for me real quick?
Got negative 7.43 times 10 to the third.
Yeah, so this is roughly minus 7.5 kilojoules per mole. Right, so the system does a ton. Compared to delta H, there's a lot more delta U, right? If this is negative, that means delta U is larger than delta H. So the system does much more. In this case, the system it consumes much more energy or releases much more energy because you have to convert from a physical form to another physical form, right? There's the work being done, which is the idea of taking 2 moles of H2 and a mole of O2 to form H2O, right? But there's also that's going to generate some heat, right? Or absorb some heat, whether it's endothermic or exothermic. We'll come back and calculate that next class. We're not sure what delta H is, how much heat's being released. But what we know is that delta U is much, much greater than delta H because you're negative 7.5 kilojoules per mole, right? So that means delta U is much greater than delta H, which means that most of the energy running through this process is being used to convert 2 gases into a liquid. Not for the chemical reaction itself, not for the heat being released from that process, but rather that you're taking something that has the PV, right, the pressure and the volume of a gas, and condensing it into something that has much less volume and much less effective pressure on the system. Right, so the system releases a lot of energy in terms of work to convert from gas to liquid. So when you talk about chemical reactions, and we think about, okay, how much is being used for heat and how much is being used for work, well, it very much depends on the physical form of the reaction. Right? If we have a system that's moving from a very similar form to another form, to a similar form rather, right, crystal to crystal, very little work is being done, so most of the energy being generated or absorbed is being put into the enthalpy part, right, into the heat. But if we have a significant rearrangement of the system in terms of its structure, then the total amount of energy change in the system is going to be much more in terms of the work being done into the system than it is about the heat being released. Okay, so let's hold on to this idea that the difference between the amount of work being done is 7.5. The question is what's delta H here, right? How much heat is being released by this reaction? We haven't quite gotten there yet. So what we're going to do on Thursday is we're going to come back to this reaction again and talk about, well, how do we calculate delta H for this product, for this reaction, right? And then we can get a sense of how much is being done as heat and how much is being done as work. Okay, have a lovely day. Office hours tomorrow from 11 to 1. Those are really for the other section, but you guys can come if you want. And then Thursday, I'll extend my office hours from 11 to 3. So you're welcome to come anytime during that period on Thursday.